Hi, welcome back. In this lecture I want to talk about complex matrices. That is nothing else than matrices with complex elements. In particular, I want to talk about multiplication between matrices. At this point in your education, I'm sure you already encounter complex matrices, or at the very least matrices. So complex matrices are nothing else than matrices with the elements that are complex values. So in this particular slides, we have a complex matrix A that consists of a number of elements structured in the matrix, with each element belonging to the complex. We can define operation such as addition between complex matrices in the very same way that you will do with real matrices. So in the case of addition, we just add element by elements the elements of the matrices. So this one with this one, this one with this one, and so on and so forth, obtaining this value here on the slides. Together with addition, we can also define a multiplication of a scalar C with the complex matrix. So it is nothing else than multiply the C scalar for each element of the complex matrix. So these are kind of elementary operations. So probably the most interesting operation is called matrix multiplication. So this also will be a way for us to we will use matrix multiplication, for instance, with a vector or between two matrices, to express operation by so-called quantum gates. We will see later on, we will express quantum gates operation in the form of matrices, and then we will make usage of matrix multiplication to understand quantum computation and understand quantum gates acting on quantum states. So how this is working exactly the matrix multiplication we do with a real number. So when we want to calculate an element of our matrix multiply, for instance, we have A and B. We start for calculating each element of the multiplication of the two matrices. And the way to do that, we basically take an inner product, or this sum of the multiplication or element of the first row. If you calculate this element here, multiply by the first column. So the first element here will be first row multiplied by the first column of B. If we take this element here, we will take the first row multiplied by the second column here. So we go through each element and then we apply this under product and calculate the full matrices. This is very similar to, is identical to the matrix multiplication that you already know. It's just an extension with a complex number. Remember, when we have a complex number, you might multiply I by I, and this is going to give us imaginary term. So nothing difficult, just a recap of what you already know. I'm also sure that at this point you also know the so-called identity matrices. The just is a matrix that if we multiply any matrix, we obtain the original matrix. So this matrix has all one along the major diagonal. A matrix multiply have these very important properties. Is associative. It does have an identical matrix, and it also have distributive properties over the addition, and also the matrix multiplication respect scalar multiplication. So these are four major properties that matrix multiply has. So associative, he has identity matrices, multiplication has respect distributed properties over addition, and then respects also the scalar multiplication. In addition, there are these other three properties for which we will need to introduce additional operation that we'll see in the next lecture. Note an extremely important lack of a property that in the matrix multiplication is not commutative. So this is very important. So A multiplied by B, where A and B are matrices, is not equal to B multiplied by A. So extremely important here. We can introduce the concepts of complex algebra, a complex vector space V with a multiplication star that multiplies two matrices. Satisfy the first four properties that satisfy the first properties is called complex algebra. So if we satisfy these four properties, then we are dealing with the complex algebra. Complex matrices can be also called maps. So for instance, if we have A multiplied by B for any elements of B, we are going to have that these results in the element of will be a complex matrix. In other words, multiplication by A gives one function from C to C. We saw in the previous slides that this function preserves addition and scalar multiplication, and we will write this map as following. So this is a map that is arising from multiplied by A from C n to Cn. We also talk about linear maps when the maps satisfy these two properties. So we have respect of the addition that is shown and expressing this here. So our map F acting on V1 plus V2 is equal to our map F applied to V1 plus our map F applied to V2. So we can split it. Also, F, our map, can respect the scalar multiplication. So if we have our map acting on C multiplied by V, we can bring out C. So this will be equal to C multiplied by our map applied to V. When these two properties are respected, then we are talking about linear map. We are going to talk about operators, quantum computing operators. Quite often in this course, I want to provide a more formal definition. We will call any linear map from a complex vector space to itself an operator. So if F, our linear map from Cn to Cn is an operator on Cn, and A is n by n matrix such that for all V we have our operator on V is equal to A multiplied by V, then we say that F is represented by A. So this is extremely important part for this course. We will express our quantum computing operator, or in many cases like a quantum gate with the matrix A, and this will represent our operators on a certain vector that will represent the quantum state. So to make evolve the quantum state, we've applied a quantum gate that is represented by a matrix A that is applied to the vector representing the quantum state, and we can describe the evolution of the quantum state as a combination, as an evolution of several matrices that are multiplied by a complex vector. As I said, it's particularly important. We will use complex matrices to represent quantum gates. So we will study how to represent the particular elements of these matrices, and then we will see that we can represent the acting on a quantum gate on a certain quantum state, just multiplying the complex matrix to the complex vector. So this is the last slides of my lecture, and talk to you soon.